Eduardo, please.
Yeah, of course, for you it's new what how the climate looked like over the 2000 years. For me, it's not new because I'm 2000 years old almost. So everything what I'm going to tell you, I was experienced directly. So do you have renewed energy after the break? Okay, then we change topic a little bit and we go to paleoclimate from reconstructions, that's from proxies and from climate models as well. And before we go into the last 2000 years, which is a very, very recent past, I have two slides showing you, let's say, a broader time scale. And so that for you, perhaps interesting to know how was the temperature evolution over the last 70 million years. So it's a much longer time scales. This is something where the film Jurassic Park was filmed around this period. And this is a reconstruction of something like the surface temperature of the ocean at high latitudes. And what you can see immediately is the cooling trend in the last almost 100 million years. And this cooling trend is thought to have been caused by CO2 concentration. Here in this period it was much, much higher than today, several thousand parts per mil in the atmosphere, whereas we have now roughly 400. So that actually the concentration has gone down quite rapidly, and also the temperature. In this period, so before 30 million years, roughly, there was no permanent ice at all. Either Antarctica or Greenland, there was no ice. It was ice-free. That means that the recent period, geologically seen, is one of the coldest of the Earth in the last 100 million years. So we're living in a very cold period with permanent ice in some areas, which is exceptional in this sense. So 30 million years ago, the glaciation in Antarctica started. So the ice sheet started to build up. 5 million years ago, the glaciation started in Greenland, so in the northern hemisphere. And now I'm showing you a shorter time scale, so the last 500,000 years. Roughly. We had a new phenomenon in this time scale, which is the wane and grow of the ice ages. This is a very recent phenomenon as well. In the last, as I said, the last 4 or 5 million years, the period of these ice ages was more rapid than now. So it was about every 40,000 years. Now in the last million years, the glaciations occur every 100,000. So it's roughly quite regularly. And we are now in a warm period, so within those glacial periods. So for you to have an idea, probably you know better than me, but just I say it for the whole audience, to have an idea about the difference between a glacial period and an interglacial, a warm period like today. It's like yesterday we could sit in the barbecue here near Stockholm, and 20,000 years ago, which was the maximum of the last ice age, we had here an ice sheet of about 3 kilometers height. So we'll be barbecuing covered by 3 kilometers of ice. And the sea level, so here you have the oscillations of, sea level here. So we see every 100,000 years, the sea level dropping because of the build-up of the ice sheets. So the range is about 120 meters difference. So the next time that you are on the beach and look at the sea, you can try to imagine how the landscape would look like if the sea level would have dropped 120 meters. And that happened not very far away, not very long ago, about 20,000 years. It's not very, very long in its history. So the landscape in the northern hemisphere, of course, was very different than today. The vegetation was over Europe very different, so no forest, almost tundra over whole Europe, etc., etc. The CO2 concentration also oscillated with the ice ages. It dropped during the ice ages to 180 parts per million. In the parts per mil, sorry, in the warm periods, it was about 280, as we said. One important aspect is that plants can only survive below this concentration of CO2, 180. If the CO2 concentration drops below that level, there will be no photosynthesis possible. So we are here already at the very limit of sustainability of the planet. Okay, that happened over the last million years or so. Now we go to a shorter time scales, closer to now. These are reconstructions of, well, winter and summer temperature in Europe, north, south, west, and east. In the last, let's say, 10,000 years. So the time is running in this direction. Here is all the time, here is present. And we see, for instance, in the north, a cooling in the summer temperatures. So the summer temperatures were warmer about 5,000 years ago than now. This is the so-called mid-Holocene optimum. In southern Europe, it's not as clear. The reconstructions are also more uncertain. They are based on pollen remnants. Yeah? And the seasonality is also a little bit unexplained. But generally speaking, it seems to be roughly clear that the mid-Holocene, so 5,000 years ago, was a little bit warmer than the present climate in the northern hemisphere, at least. Sometimes this argument is used to say, okay, climate change is not important because it was already a little bit warmer in the past. This argument is wrong, because actually what we know why the mid-Holocene temperatures were a little bit warmer. So as we will see, the forcing factors were a little bit different. For today, the problem is to explain the warming that we observe today, right? It's like saying, unfortunately, some person died yesterday somewhere from illness. And said, okay, well, we have to worry about, perhaps there is an infection going around, we have to know why that happened. That would be the reasonable stance. Or you could say, well, okay, 500 years ago people died everywhere, so could be natural causes. So you see the wrong argument there. We have to explain what happens today with the forcing factors of today. And we need CO2 for that. Okay. Now we go into the last, well, in this case 1,000 years. I will show later a little bit a wider time scale covering the last 2,000 years, but most of the work of the late Holocene climate has been done for the last 1,000 years. And this is because the proxies that we have to reconstruct the climate, which are basically tree rings, the coverage is much better for the last 1,000 years than for the last 2,000 years. But nevertheless, recently there are reconstructions aiming at that period. And what we see, these are several reconstructions based on different proxy data. We'll explain later how the temperature is a little bit, can be reconstructed. They disagree, of course, as usual in climate, not all of them, but they tend to show warmer, relatively warmer periods 1,000 years ago. And this is the so-called medieval warm period, then a cooling into the Little Ice Age, let's say 1500, 1600, 1700. 1700 was probably the coldest period in the Millennium. And that's why all the paintings in Holland were made with ice-covered boards and people skating on there very often. That was really, there is historical evidence of very cold temperatures around 1700. And then we have this very rapid warming in the recent period. So let's have a look at how the temperature can be reconstructed, or the climate in general. And for the last period, as I said, for the last 2,000 years or a few thousand years in the Holocene, tree rings are the best proxy. So you have a very big tree here. They can grow very old. Some of the oldest living trees are, I think, 4,000 years old that have been found, I think, in northern Sweden, could be. But you don't need trees that have lived that long. There's a trick to reconstruct temperatures back in time with dead wood already. Yeah? And we will see how it's done. Well, of course, we have to have a biological system that is sensitive to temperature. And the tree ring width usually is sensitive to the growing season temperature. When it's warmer, the tree rings are wider, grow wider. When it's colder, then they are narrower. And of course, we need allocation. So, for instance, northern Sweden or the Alps or Canada, where the trees are growing at the edge of their living range. So they are sensitive to temperature. A tree in Spain is not sensitive to temperature at all. It's happily living. Doesn't matter if it's a little bit colder or warmer, but doesn't matter at all. Temperature is not a limiting factor. But in the Alps, or in Scandinavia, or in Canada, or in the Andes, or in the Tibet, trees grow at the very edge of their living range, and so they are very sensitive to temperature. In summers that is very cold, they don't grow, and you can see then this pattern of tree ring width. Imagine that we have a living tree, so we know this year exactly, and we will go back in time. This tree has died, let's say, in 1900. Now we find in a lake with anoxic conditions somewhere another tree trunk that shows also some growing patterns, but we don't know when that tree actually died. We found that tree, but we can try to match this pattern with the pattern of the living tree. It's like a barcode, and we shift this pattern backwards and forwards until we find a match there of 30 years, for instance, in the overlap period. Then we say, okay, we can date, then also find when this tree died. And we can continue back in time, and in the end, build what is called a chronology of tree ring width, and with that, reconstruct the temperatures at that site over several thousand years. Right? This is the principle. There are other types of proxies that I wanted to show, okay? Yeah. There are other types of proxies, not only tree rings, but for instance, you have lake sediments in which they may be laminated, and some concentrations of some chemical compounds or isotopic differences in these vast sediments can give you information about past precipitation, for instance, concentration of calcite, something like that. In corals, that also can grow very, very old. Dead corals that are very old. You can look at the differences in the concentration of oxygen isotopes, oxygen 18 against oxygen 16, which is sensitive salinity and temperature conditions of the coral. So that can you reconstruct the water temperature, for instance. And we have, of course, in the recent period, historical documents. They are also very important. And there are a lot of groups that go into the libraries and look at very old medieval reports of let's say doctors or priests or clusters, and they look at references. For instance, this winter was so cold that the lake was frozen for over 2 months, something like that. That accounts, and you can then derive the temperature, the mean temperature of that winter. And that goes about 500 years or so, something like that. And they can be quite accurate. And also they can be quite interesting because they record extreme events. For instance, in these historical documents in Switzerland are very, very rich. And they record flooding and droughts and extreme temperatures very, very well. And they agree up to the year very, very well. Okay, what are the, yeah?
Can we reconstruct from glaciers?
Yeah, well, yeah, it's also possible. Mostly the isotopic composition of ice. Oxygen 18 to oxygen 16 is well sensitive to the origin of precipitation of the glacier, but also to the overall temperature as well. Yeah, but that's a good question, because we also need to reconstruct the forcing factors to understand climate change. And there are different forcing factors that are important for the Holocene. One is the orbital configuration of the Earth. Has not been constant all the time. It changes. The Earth is like a spin, like a top spinning around. You can imagine that's spinning this way. The axis is also spinning in this way, and the orbit is also changing, the eccentricity of the orbit. So we have these three different movements that changes the amount of radiation and the seasonality of the radiation that impinges on the Earth. That, of course, is important for very long time scales, for millennial time scales. And we saw that this cooling in summer temperatures since 5,000 years ago until roughly today is caused by exactly one of these changes in these parameters. We will see later which one. The solar activity is not constant, so the energy output of the sun is also changing, is not constant, it's changing all the time at all time scales. And it is believed that the Little Ice Age and this drop in temperatures around 1700 was partly caused by a low activity of the sun. Now the sun seems to be, well, the activity of the sun has been growing over the last 20th century, and it seems to be dropping now. So the sun is getting a bit weaker, and there are some voices that say, well, we have to be a little bit careful because the sun can get weaker for the next 20 years or so. It could be colder, but it's believed that this effect will be in any case small. We have anthropogenic greenhouse gases, of course, also the natural variations, but recently the anthropogenic emissions that have really brought the CO2 concentration out of any natural range of the last million years. Now we have 400 ppm. The natural range was between 180 and 280. So we are now way above the natural range of variations. And a very important factor also is volcanic eruptions. Volcanic eruptions tends to cool the climate for a few years. And they can be, sometimes if they are big, they can have a very strong impact on the climate. For instance, the one big eruption, the Tambora eruption, 100 years ago, in 1815, caused a global cooling, which was perceptible in all historical records and agricultural productivity worldwide. And it was actually a moderate eruption. We know that there were much bigger eruptions within the past millennium. So how can we know all this? How these forcing factors change? Mostly from ice, from the ice cores in Greenland and Antarctica. How can we know the CO2 concentration of the past? Because when the ice forms in Antarctica, it traps air bubbles. And we can find these air bubbles again that were encapsulated, the oldest one, 1 million years ago in Antarctica. So we can analyze the CO2 concentration of that time directly. And we know the CO2 concentration at that time. How can we know the solar activity, the past solar activity? Also from ice. So the sun has a magnetic field that shields the Earth, protects the Earth from galactic cosmic rays. When the sun is weaker, this magnetic field is weaker, and we have more cosmic rays impinging into the Earth's atmosphere, and they produce more carbon-14, this isotope that is very well used for dating. And we can see that in tree rings as well, and also some other isotopes like beryllium-10 that we can see in the ice cores. And from there we can derive the past solar activity. So it's actually a tricky volcanic eruptions. Also looking at the ice. When a volcano erupts, it liberates a lot of sulfate that it's transported in the atmosphere, and deposits into the ice. That changes the pH of the ice, the acidity. We can measure now the acidity and see that changes in acidity are synchronous very often in Greenland and Antarctica. That can only be due to volcanic eruptions in the tropics that have extended all the aerosols and sulfate. So for instance, this is just an example of an ice core, and you can see the annually bands of the ice core so that you can date the ice core without any carbon-14, just counting the layers in the ice to the year. And we can see, for instance, in 1256, there was the biggest volcanic eruption in the Millennium. It was about 5 times bigger than the Tambora eruption. And we can date it to the year perfectly, or almost perfectly. So corals, said you. Now, let's have a look at more detail at the orbital variations, so to understand this Holocene cooling. As I said, this is the Earth. We have this movement spinning, then the axis is moving around. The angle is also variating. So the most important movement for the Holocene for the last few thousand years is this spinning, this movement in cycles of the axis of the Earth. That means that now summer, which occurs of course in the Northern Hemisphere in July, occurs when the sun is farther away from the sun. It's a little bit contradicting, but this is the sun, the Earth is facing to the sun in the Northern Hemisphere, so it's summer here, but it's quite far away. Now when the axis has rotated to this position, then we have winter in the Northern Hemisphere and summer in the Southern Hemisphere. And this position is farther away for the Southern Hemisphere. So we have a change in the seasonality, and that period has that movement has a period of about 20,000 years, sorry. So that 10,000 years ago, the perihelion, so the point farther closest to the sun in the Earth orbit, that now occurs in January, it occurred in July. And so the winters and summers, the temperature should have been different. In the middle Holocene, as I said, it occurred in July. Now it's moved to January, and that caused this long-term cooling in summer in the Northern Hemisphere. So it's just the movement of the Earth that caused this cooling. And you can see here the calculated solar insolation trends. So we'll explain this a little bit. So this is the year, the annual cycle. We start in March, June, September, December, and March again. And this is the latitude. And we see that, for instance, in summer, at high latitudes in the Northern Hemisphere, we have a strong negative trend in the insolation. This is causing the cooling. But in winter, for instance, in December, we have a positive insolation trend. So that the winters should become a little bit warmer and summers a little bit cooler over the last few thousand years. It's not easy to understand if you see this picture for the first time. It's a little bit complicated, so you have to look a little bit closer than at home to understand this. But it's actually the advantage is that this forcing can be accurately calculated. You don't need any proxy at all. Just by orbital calculations, you can calculate these trends very, very well. Now you put these trends, this orbital forcing, in a climate model, and you can simulate these trends caused by orbital forcing in each month of the year with a climate model. And for instance, let's look at... No, that can be wrong. This scale is wrong. These are all negative trends in summer. Oh no, okay. This is the July and August and September temperature trends simulated by a climate model forced only by orbital movements. And you see these negative trends in the Northern Hemisphere. now interesting point is we know the forcing perfectly. So there is no uncertainty in past, let's say like CO2 concentrations or solar activity. This is calculated, can be calculated for exactly. So the two climate models should produce the same result in this cooling, but they don't. We have here a comparison of two climate models that actually are two versions of the same model. This is ECAM 4, this is ECAM 5. It's just, well, an improved version of the model. And you look at the simulated trends caused by orbital forcing. This is latitude. Again, this is the amount of trend. And you can see that this model produces double as strong trends as this one. So even in that case, in which the forcing is completely well known, these very long time scales, these are trends over 2,000 years. They are not variability over 100 years or 50 years. That is the perfect situation to test a climate model. And even then, well, you see these differences.
Sorry, why there is a gap?
This is, oh, that's a good question. Why is this? I don't know. I will come up with a reason. Oh yeah, it is land only. Also, and this latitude there is no land. Yeah. Well, actually, yeah, there should be an explanation because it's already published. Okay, we mentioned that the sun hasn't been constant, and we can somehow reconstruct the past solar activity based on these cosmogenic isotopes, beryllium-10 and carbon-14. Now, again, we have different reconstructions. Different groups say that change in concentration of beryllium-10 corresponds to certain change in solar activity. This proportionality factor has to be calibrated, has to be estimated somehow. And different groups come to different assumptions so that the amplitude of variations are also different. The shape, as you see, so that the time evolution agrees, they are all very well correlated, but some of them assume a very, very wide change in solar activity and others very little. So that's here a problem to simulate past climate. But the important thing is that here in the medieval one period we have higher solar activity, that's for sure. We don't know how much, but higher. Then in the Little Ice Age we have a weaker sun, and then in the recent 200 years or so we have the sun has been strengthening again. That seems quite robust.
Does it mean, is it for the whole hemisphere?
Well, this is this has no relation to the Earth. It's the solar energy that comes out of the sun.
My question is then how to explain the reason for the medieval warm period.
Oh, well, that's another question.
You suggest now that at least one part is explained by the...
No, I didn't say that. No, I said that we observed warmer temperatures during the medieval warm period, and we observed higher solar activity. But I didn't make the connection.
But you showed the temperature for the northern hemisphere. Do we have any evidence for the temperature of the southern hemisphere, 1,000 year back?
Well, yeah, we have, but with a very limited set of proxies. For the southern hemisphere...
Sure, is it similar? So is the...
No, it doesn't match.
So it's a problem of the... Well, it's a feature of the northern hemisphere.
Well, it's a picture of the information that we have of the northern hemisphere, because for the southern hemisphere we have only for these time scales only terrestrial proxies, and in the southern hemisphere, well, we have New Zealand, the Andes. That's it. So the coverage is very limited.
So we do not. The answer is we do not know what happened during the.
We don't know what
period of the sun.
Exactly. Yeah. So what I said is that the reconstructions do not match, but what happened in reality. Well, and even, well, answering your question, would that explain the medieval warm period, the sun here? No, it wouldn't, because the timing is wrong. we see that in the northern hemisphere, the warming in the medieval warm period occurred around year 1000. And here the maximum in solar activity occurs actually in 1200. So about 150 years later. So that wouldn't explain that. The origin of the medieval warm period is an open question. It's not known yet. So we have volcanic eruptions as well. That can be, intensity can be reconstructed. We have again the two data sets competing that roughly agree. Yeah, for instance, you see this very big eruption, as I said, in 1256, roughly. Tambora is this one. And we had also a very big eruptions, which is unknown. So we know that there was an eruption, but we don't know where. That happens also. There are no historical accounts at this time. And, well, you can assume where it could be, but it's not certain. For instance, this eruption has been identified only 2 years ago. We knew that there was an eruption, but only 2 years ago the volcano was found, the Samalas in Indonesia as well. And you see, one characteristic of the volcanic eruption is that we had very little also in the medieval warm period, right? With a coincidence, when the solar activity was, well, higher. And we have also increased volcanic eruptions recently. It is not known why, but there is certainly a clustering of eruptions and periods that are very quiet. And it's also an open question. The last forcing that we have to take into account is an anthropogenic forcing, but it's a different. It's not CO2, it's deforestation, the change in land use, so the expansion of agriculture. And agriculture, well, it expanded, of course, very rapidly in the late millennium, the late part of the millennium, usually causes a cooling. So you are deforestating. Forests are dark areas. Crop areas are bright, seen from the space. They reflect a lot of sunlight. So the reflectivity is higher, and they produce a global cooling. Agriculture. It's not very much. The magnitude is tiny, but the models do really agree on that characteristic. And if you want to simulate the climate of the past millennium, especially in the last few hundred years, you have to include that. It's a non-negligible forcing. Okay, now we have all these important forcings. We have, so that we can drive the models to simulate the past millennium. We have reconstructions, then we can compare them. And this is just a comparison of different simulations of the past millennium, which are the color lines, and reconstructions, which is the shading, the range of reconstructions. As again, we see this, well, medieval warm period, and we'll come that now in a minute, the Little Ice Age, so this cooling, and the recent warming. So they sort of agree, right? They look similar, but here there is a clear disagreement. So the reconstructions indicate warmer temperatures in the year 1000, where the models indicate warmer temperatures in the year 1200. This is a real mismatch that, as I said, is not solved. We don't know why this is happening. The solar forcing, of course, the models are seeing the solar forcing, which is peaking here. Why the proxies are not seeing that? And they are warmer before, 200 years before. Could it be natural variability? So these random trends that we spoke before? If that is true, that the climate can produce centennial scale trends of this magnitude without any external forcing, that has strong implications for the future, because it can happen in the future as well. In both directions, warming or cooling. So it can reinforce the anthropogenic forcing, or it can ameliorate the anthropogenic force. That's a very important question in the medieval warm period for the future climate. Okay, now in the last 5 minutes, we expand a little bit the time scale. And now this is the first simulation, actually, of the last 2,000 years with a comprehensive climate model, with a sophisticated climate model that is used also for climate predictions. And here we can see all the forcings that we have talked about in action. We see, for instance, well, this is the red line, northern extratropical land summer, near surface temperature, and if you see it from here, you see this long-term cooling trend. This is the orbital forcing. We have, well, probably the sun. So this long-term evolution. We have the volcanoes. So we had here in the first millennium still a bigger eruption than the Samalas, which is here. Right? And of course, the recent warming. So now the question is, what is the model saying about the relative level of warming over the past 2,000 years? So the model is saying that the medieval warm period was not as warm as the recent period. This is clear, right? And the Roman period here was a little bit warmer than the medieval warm period, but is still cooler than the recent period. Yeah? Now we have also reconstructions covering the last 2,000 years. And this is the paper that I suggested for you to read. So you know it already very, very well. Right? This is a first attempt of this group, the Pages 2K group or network, to reconstruct the climate of the last 2,000 years. And well, the problem is that this is not a global reconstruction. These are a collection of regional reconstruction. So that was a political, well, somehow political problem, because we couldn't agree, let's say so, we couldn't agree on a common method to produce consistent, uniform reconstructions of the whole globe. So the European group, for instance, opted for a certain statistical method to calibrate the tree rings. The Australasia group or Asia group used another method. They thought that it was better. So the result is that you cannot then mix them together to produce a global reconstruction of the global mean. So you end up with all these regional reconstructions, right? So we will comment then on this after the break. Right?
So please continue, Eduardo.
So we had this graph of regional temperature reconstructions over the 7 continents, and all are based on tree rings except one, which is based on pollen records from North America. Well, you see general characteristics, right? Here in the around 1600, 1700, all regions tended to be cooler, to be cool. And before that, all regions tended to be a little bit warmer, right, and over the Little Ice Age. However, there are differences. This warming in the medieval warm period was not synchronous in all regions. For instance, here in Asia, you barely see it. In Europe, with Europe, well, a little bit. In North America, it's very, very clear. In Antarctica, well, Antarctica is a little bit special case because it's just only one record from one ice score. So the reliability of this reconstruction is a little bit contested. But, well, the message is that this medieval warm period probably was not global. It appeared at different times. Could be an indication that it's internal variations. Has nothing to do with external forcing, or very little. That would be an indication. Whereas here, the Little Ice Age is much more homogeneous across all regions. And that could be an indication that it's the weaker sun and the more frequent volcanic eruptions at the same time. For some reason, this is an interesting story, for some reason, solar activity and volcanic activity appears correlated in the proxy records. And for unknown reasons. Actually, both systems have nothing to do with one another. But there's a very clear, statistically significant and very suggestive correlation. And the reason is unknown.
Sorry, for how long period of testing?
Well, for the last, let's say 1,000 years, a little bit longer. And interestingly, now I mentioned at the beginning that the sun is getting a little bit weaker in the last 5, 10 years, and volcanic eruptions are getting stronger. We have now recently more volcanic eruptions again. So that would be an interesting topic for our proposal. Would be. Well, now let's look at some of the longest reconstructions. For instance, Europe. It was in the one that I was involved, and you see that suddenly that Europe shows very warm temperatures 2,000 years ago. And this is the time series of the European reconstruction. I show here two lines. Well, there are two different statistical methods, but you see that they agree very, very well. So you see the medieval warm period, which is also composed of several maxima, the Little Ice Age, and the recent warming. Again, one topic of discussion is always the level of warming. Was it warmer in the past as today? This reconstruction says that it was not warmer in the medieval warm period, but it was clearly warmer over the Roman times. And well, if you see Hollywood films in which about Roman contest, you see that all the Roman soldiers are very lightly dressed. So that must be a grain of truth in, in that reconstruction. Well, that would be also an interesting period to analyze. What are the reasons for this warming? It doesn't show up really in the forcing either. So we could have two candidates of very strong natural variations. It could be that the reconstruction is wrong. So there are uncertainties there. I didn't plot them here, but there are, of course, uncertainties. Now, we can ask yourself questions about what was the warmest year over the past 2,000 years in Europe. And that's what I'm showing here. This is a somewhat complicated plot. These are the ranks of the year. For instance, number 1 would mean the warmest year of the millennium, or the warmest summer. These are the two methods. Just look at the left side. And you see that according to this reconstruction, the warmest year was still the last one of the reconstruction. It's 2003. The very warm European summer that we all experienced. Do you remember that? Or were you born at that time? Yeah, well, it was one of the, well, there were, and in France, in Switzerland, a lot of casualties due to the heat wave. In this reconstruction, this year, this summer was the warmest over the past 2,000 years. But immediately, rank number 2 is, one of the years of the Roman period. So we find years that were almost as warm as the recent one. What was the reason? The forcing, it wouldn't have the CO2 forcing. The solar forcing is unclear. It was that warm. So it's not clear why these very warm years or very warm summers occurred. Again, over the medieval warm period, we have also some extreme years, not that extreme as before. And for the coldest summers, we have the reverse story. So the coldest summers occurred during the Little Ice Age, very clearly, around 1700, 1600, 1650. Well, it's difficult to explain this pattern. Of course, for the last period, we know that CO2 forcing is contributing. There's, of course, completely sure. For this period, we have to really analyze the simulations and compare with the reconstructions and see what is happening there. So this is research going on still. Now we can compare the simulation and the reconstruction. I showed you before the plot of the simulated European temperature, and we have here both the simulation and the reconstruction. So we can test if the model is being realistic or not. Overall, you see that it looks quite nice. And there are really two completely independent sources of information. When we did the simulation, we didn't take into account any data from the proxy data. Actually, we didn't have them. So the simulation started before the reconstruction. They are completely independent. And they actually, well, they agree quite nicely. The range is, well, not exactly the same, but it's similar. You have to consider that the blue line is just produced on a computer, right? And the red line is from tree rings. So the agreement is quite remarkable. If you look at now at these very long frequency variations, they also agree quite well. Yeah. If you look in more detail, for instance, the volcanic eruptions here, they disagree. Well, they not agree so well. Simulations sometimes produce a very strong cooling that is not seen in the reconstruction. These volcanic eruptions and simulations is also quite important for the future, because a volcanic eruption represents a very strong perturbation of the climate system, and it can be used to test the models. How good are models to simulate perturbations of the climate? And that has been done for the Pinatubo eruption, quite detailed way, because for the Pinatubo we have a lot of observations. And there has been many simulations that can be compared not only with reconstructions but with real measurements. And for the Pinatubo, there's a very good agreement. But once you go to past eruptions, and this one was very, very big, was much bigger, 10 times bigger than Pinatubo, for instance, then you see that the models do not agree so much or so well. Could be that the tree rings are not reflecting the amount of cooling, because for instance the cooling was so strong that they reached the minimum amount of ring width that they can form, so that you have a threshold in which the trees cannot represent cooler temperatures. Could be. So there is a reduced range of variability. Could be that the models are too sensitive, or could be that the forcing is a little bit too strong, or could be something different, as we will see now. Could be internal variability, as usual. It's always lurking around this animal, right? I show you here now an ensemble of simulations of the past millennium. Here we have 10 simulations, I think, 10 simulations. Here we have 3 simulations with a different model, and they do not go right to the present state. But actually we are only interested in this past millennium. In this case, it's exactly the same model as before, only the initial conditions in year 850 were different. But other than that, the forcing is the same, the model is exactly the same. So we can look at individual volcanic eruptions and see if all the simulations produce the same cooling or not, or there is some internal variability. That's what is hopefully is shown not here. The next one, yeah. I have chosen here 2 volcanic eruptions, so 2 periods: the Samalas in Indonesia that occurred in 256, and Tambora Tambora here, 1815. This is the one climate model, the American one. This is the German climate model. We have here 9 simulations, and here 10 simulations and 3 simulations. And we can see here directly, or we can test directly if all the simulations agree, and they don't. You see a range in the cooling. The cooling goes here for the Samalas from 1.1 degree cooling to 1.4 degree cooling. So it's a wide range. It's 50% almost. That means that even in this case, in which the external volcanic forcing was so strong, so very strong eruption, the random internal variations are again modifying the response, so that some simulations produce this 1 degree cooling, other simulations produce much more cooling. So that could be also an explanation for the difference between model and reconstruction. The reconstruction has its own internal variability, and the model its own internal variability, and they are not synchronous. So that could be the explanation. For Tambora, of course the cooling was smaller because the eruption was also weaker, but the range is also quite substantial. Minus 0.6 cooling or 1 degree cooling. It's quite substantial. And here we can also compare with some observations in 1815, so that we wouldn't have the problem of the sensitivity of the tree rings. And it seems that nevertheless the models are overestimating the cooling. So the observed cooling was not as big as the models indicate, although it was quite substantial, and can be really seen in the meteorological records as well. So that could be an indication that the models are a little bit oversensitive, but 2 or 3 question marks behind that. It's quite speculative. We also see that the recovering time after volcanic eruptions is roughly 10 years. So after 10 years without any volcanic eruption, then the climate has come back to the original temperature. But 1 degree cooling actually is very strong. I mean, if we have this type of eruption again, well, you will remember that talk very well.
Where is the memory coming from? Is it the upper ocean?
Yeah. It's basically the upper ocean. Yeah, you can see that if you look at the, let's say, the lifetime of the perturbation over land is much shorter than over the ocean. And over Western Europe is longer because it's affected by the Atlantic Ocean, and Siberia is much shorter. Well, again, similar story for when you go to regional scales. I showed you before the global mean temperature, and now we look just at Europe. And we look also at the internal variability in these 2 eruptions, Samalas. It's only Samalas. This is the longer time scale, so 1 century, and this is just 15 years. Let's look at this one. So the 3 simulations by the German model that all cool according to this volcanic eruption. But you see that, well, I mean, in the green line, if that was reality, you could see, well, 1 year was colder, but it could be random. I don't know if that would be a volcanic eruption. The black line, for instance, produces a more consistent cooling. The red line is something in between. So when you look at the European scale, of course, these random variations become more important relative to the forcing. Now, if you are trying, for instance, a study to compare reconstructions over a very limited area, the Alps, for instance, compared to the models, that's a very, not a very good idea. Already, because probably if you have an agreement, it may be just by chance. You have a disagreement just by chance. It's only a grid or 2 grid cells. Yeah, we can have a look at the effect of reconstructed temperatures of volcanic eruption. This is the Tambora eruption this year, actually. Well, it is the next year of the eruption, because actually in Europe the temperatures were a little bit colder the year later. And we see a strong cooling over France and actually a warming in Eastern Europe. Does anyone have an idea why this pattern may arise? Why we have here warming over this area? Some hint? Well, the reason is that the volcanic eruption does not only change the energy balance locally, but also changes the atmospheric circulation. So all these aerosols floating around in the troposphere and the stratosphere, they change the wind patterns, and they change the NAO pattern, the North Atlantic Oscillation. So after volcanic eruption, the North Atlantic Oscillation tends to become a little bit stronger, and this causes warmer temperatures of this area. So that volcanic eruptions do not produce an overall, well, globally seen it's a cooling, but regionally the response may be different. Now, if we compare that with an ensemble of simulations, we have now these 3 simulations with the Max Planck Institute for the Tambora eruption. Well, look at the different responses. This is the same model, the same forcing. Well, they are very different patterns of temperature change. In the ensemble mean, well, of course they average to very low values. Of course, the ensemble mean will not, is unrealistic, because this is well, that would never happen. It's just a mean of 3 possible trajectories, each of which could happen. But ensemble mean is just an artifact, an statistical artifact. So the message is that the regional variations can be very large. And that's what I said. If you are comparing reconstructions of the effect of volcanic eruptions over Switzerland and compare to models, well, that's clueless. Okay, another example of model and reconstructions and the role of internal variations is this. Well, this study that I actually found quite interesting. I didn't do the reconstruction part, only the modeling part. What they did, this group from the University of Stockholm, was to reconstruct the winter temperature in Stockholm. And this is based on historical documents. This is an example of how the climate can be reconstructed from that information. It's interesting because to reconstruct winter temperatures is very difficult, because biological systems responds to the growing season temperature usually, not to the winter temperature. So there are very little information about past winter temperatures, but in this case it could be achieved from historical documents. And what they had in the archives in Stockholm was the first date in which a ship sailed out of the port in spring. Usually at that time it was, I think, something like April, May. It was the first time in which the port was ice-free, so a ship can sail out. And they have a record from, I think, starting in 1700 roughly until today. And they took the last 100 years and calculated the correlation of this sailing date to the winter mean temperature as recorded in the meteorological stations. And they saw a very high correlation. So they could extrapolate this relationship into the past and reconstruct the winter temperature in Stockholm. And this is the result. This is the black line. Well, actually it goes to 1500. So you see these variations. Colder period around 1650, so it doesn't match really with the Little Ice Age that was recorded with the summer temperatures from 2 rings. A warmer period around 1750, and then a very long warming trend of the winter temperatures. And the other color lines are the models. 3 simulations actually. And if you look at the long-term trend, actually it's very good. If you calculate this trend over the last 400 years, they agree really good, really well, surprisingly well. But you have here a period around 1750 in which the winter temperatures in Stockholm tend to be warmer relative to the trend. And the models are not able to reproduce this. If you look at other temperature reconstructions of that period, for instance, the central England temperature, which was also based in historical documents. You also see that these decades, 17 to 1750, were actually warmer than the previous period and later period. What was the cause of this? Open question again. The solar forcing is peaking. It had a maximum, but later, not in 1750, but in 1780, so later. So we have a period, about 30 years, or multi-decadal period, in which the trend was, in Stockholm, I'm talking about local trends, could be a warming of almost 2 degrees in the winter temperature over 30 years. That is not related to the forcing, so the probable candidate could be natural variability. And again, the message is that could happen here again. Reinforcing the warming, the CO2 warming, or dampening it. It's a very strong trend. It's 2 degrees over 30 years, caused by probably natural variations. Of course, this is just a local record, just Stockholm. But for impact studies, you are interested in local records. So you have to take into account that the range of projections have to be widened to take into account this possibility of a warming or a cooling just due to internal variations. Well, I think I'm going to finish now with the 2 last slides. I'm going to say something positive now about climate models. So this is the NAO pattern. You are very familiar with that. This is the sea level pressure seesaw between Iceland and Portugal or Spain. So this is a typical winter mean sea level pressure pattern, the North Atlantic Oscillation. We have also a hemispheric version. This is the Arctic Oscillation, which is, well, similar to the North Atlantic Oscillation, but including the Pacific. So you have these 3 centers of actions. In the Southern Hemisphere, we have a similar pattern as well. It's the Antarctic Oscillation. All these are the result of a principal component analysis of model data. And they look really, really very, very realistic. If I would show you now the observations, you wouldn't be able to tell which is model, which is observations. They are really good. One reason is this is a large-scale dynamical phenomenon, and that for that the models are really good. They don't need the small-scale information. It's several thousand kilometers across. Only the dynamical equations are involved. So they are the best conditions for climate models, and they are very good. We have to recognize that as well. Now we can ask ourselves, how will this pattern evolve in the future or in the past? Does it respond to external forcing? We have seen that the observations indicate a response to volcanic forcing, but in general, does it to greenhouse forcing or to solar forcing? And what we did here, we just compared the North Atlantic Oscillation Index across many, many models of the past 1,000 years. And again, you see that all of the models disagree. If there were a response of the North Atlantic Oscillation to external forcing, all these lines should show the same pattern, but they all disagree. So the message is the NAO over the past millennium is just random variations, random stochastic internal variability. With the possible exception of volcanic eruptions, which are very punctual and just for a few years. Okay, now I'm seeing that you are sleeping and you are hungry, so I'm going to summarize now, actually taking into account both presentations, so the modeling and the paleoclimate. And the main message would be that, well, models have to be improved, and my hope is that they will be improved in the next years, the next decades. There is some work to be done, clearly, but I mean, it's not hopeless. We have to because we know that the climate change, if CO2 concentrations continue to increase, will happen. So we need those climate models to estimate the climate change. If they are not that good as we hope for, okay, we have to work more. The message is not at all that climate change will not happen. Only we need better tools to estimate that climate change. But also we have learned that the role of internal variations is very important, perhaps more important than was thought a few years ago. And we have also to take into account for the projections, to avoid, well, also to provide better projections, a better range, a more realistic range of possible future paths of the temperature. We have to do that because otherwise, for instance, we can insist that, as has been done in the past, unfortunately, that temperatures will steadily go up all the time. That was the message that was heard 10 years ago. But suddenly we see that perhaps they flattened, or some locations they cool. So the way up to the warming is contaminated very strongly by natural variation. So there will be periods of no warming, perhaps some cooling, then a stronger warming again. So that message has to be also provided to the policymakers. The warming will not be just steady all the way up. But if the emissions are not reduced, then there will be warming for certain. Okay, now you can wake up for lunch. And well, thank you very much for your attention.